Hello everyone. I am excited today to show you the progress that we've been making on the Terran R rocket and the overall Terran R program. We have been heads down. We've gone from initial designs through critical design reviews. We're building a lot of hardware. We're excited to share that with you today. We've really transitioned from development into building actual flight hardware now, and we're going to show you examples of that, from the primary structure, the thrust structure, the barrels, the domes of the rocket, the avionics that control the rocket, the avionics boxes, harnessing, the software that we write in-house to control the rocket during its flight, fluid systems, COPVs, and then the testing systems that we use, both for the rocket and for engines, our launch site at LC-16. In addition to the primary rocket itself, we're also making outstanding progress on the flight intent engines, testing them daily in Stennis. We're also thinking about scaling of the rocket and developing our supply chain, developing our production capabilities, our transportation capabilities to move this large vehicle across the country. And so with that, we see all of the pieces of Terran R coming together. So there's no doubt about it, we have a long way to go, but I do believe that we have all the foundational elements necessary to succeed. We have an outstanding dedicated team. We have solid financial footing. We have flight hardware that's coming together, flight software that's coming together. We have the infrastructure necessary to build the first and then many more rockets, from our factory here in Long Beach to our test center in Stennis, Mississippi, to our launch site at Cape Canaveral. So 2025 is the year in which we build the first Terran R rocket, but we're not just focused on that first flight. We are developing the supply chain, the manufacturing tools, the testing and launch infrastructure that will support a high cadence of reusable launches. So now I'm going to hand it over to more of the great leaders here at Relativity to share the great progress that they've been making. I hope that you're proud of what you see. I know that I am.
We've only been working on this launch vehicle for about 1.5 years. And within the 1.5 years that we've been working with this small team, we've really gotten this vehicle through conceptual design review from a clean sheet. We've gone through preliminary design review, and now we're in the middle of critical design reviews, which is kind of our finalization of the designs, and the engineering drawings are getting released. As of today, the primary structure is all designed now. It's all being manufactured and in work. The vehicle overall doesn't mean the whole vehicle is designed, but we're about 50% of the way through critical design reviews. It's actually the vast majority of the committed mass of the vehicle. The remaining work that we have is mostly secondary structures and commercial off-the-shelf hardware.
The past few months of the Terran R program have been the most exciting to date. We have a huge amount of flight hardware that is now being produced, and we're going to show you. We have domes that are being processed and prepared to be installed into the barrels. We have barrel sections that are being welded up from formed sheet metal.
And then we have circumferential stir welding being stood up in short order.
Flight intent engines are being produced in-house, from printing through machining, assembly. COPVs have arrived on site and are undergoing processing and testing. We have fluid systems, the assembly of our piping systems throughout the rocket that has begun.
We also have a lot of the tank barrels being welded day by day, and the stringers, the stiffeners are being welded.
The thrust structure is being assembled from its component parts as we speak. Great progress is being made there.
So the first vehicle is really coming together. Let's go over some of the architecture from the aft end to the fairing. The first stage, on the very aft end, you'll see 13 engines. They're LOX methane, and their gas generator cycle as well. Our liftoff sea level thrust is 269,000 pounds per engine. The first stage engine nozzle ratio is 25:1. Vacuum thrust will be 323,000 pounds. Our main chamber pressure is around 2,500 psia. Mixture ratio is about 2.78.
In building Aeon R, we draw heavily from the additive heritage of the Aeon 1 engine program that we used on the Terran 1 rocket. The vast majority of Aeon R is built of 3D printed parts that we manufacture in-house.
You know, we're leveraging that experience and really scaling the Aeon 1 engine from the Terran 1 program up to a much higher thrust capacity. 9 out of the 13 engines are going to be gimbaled. 4 of them will be fixed, and also you'll see 4 landing legs in their engine fairings. And the landing legs themselves, you'll see 4 of them with a sliding track for the upper strut. As you go further up the rocket, you'll see the methane tank on the bottom for the first stage, and then you'll see a liquid oxygen tank and 4 non-deployable grid fits. So both tanks on the first stage and the second stage, all the tanks actually, are going to be made of 2195 aluminum. But for the first stage, we're going to be using 2196 stringers, welded stringers, Z-stringers actually, welded Z-stringers for stiffening. For the first stage, we found that welded stiffeners were the most mass-efficient way to achieve the required buckling we needed for that tank. The downside to welded stiffeners, though, is that it adds a lot more welding and hardware into the tanks. On the second stage, we can avoid that by having the integrated orthogrid structure milled directly out of the flat aluminum panels that we get. And then the interstage will be an aluminum interstage, and the second stage will have a single vacuum engine that's also a gas generator cycle, and the fairing will be a carbon composite fairing.
In its reusable configuration, Terran R will be capable of carrying 23.5 metric tons to low Earth orbit, and future upgrades will allow us to carry even more mass to orbit.
We're not interested in only making and developing a singular boutique rocket. The thing that really drives us is making a commercially viable product that can be produced. And I think that's a big part of the reason why we're willing and able to make the pivots that we are making on the manufacturing side.
At Relativity, we use a hybrid manufacturing approach, where we use the best of additive manufacturing and traditional manufacturing. This allows us to quickly iterate during development while also scaling quickly to meet our customers' needs. The development of a rocket always requires compromises, and there's a trade-off between cost, performance, and timelines. We are actively performing that trade across the vehicle to develop the optimal rocket over time.
Ultimately, we're trying to find a sweet spot between something that's very affordable, can deliver a lot of payload to orbit, and can also be fielded in a reasonable amount of time with a high cadence as well. So there are a lot of factors that we look at, not just a single thing. We'll get more in depth into some of these trade-offs later in the video. Going back to the vehicle overview, the pressurant system will be helium. There are many trade-offs when considering what pressurization architecture you're going to develop for your vehicle. And for us, we opted for helium, and we're going to store that helium with COPVs inside the cryogenic propellant tanks. We store the helium bottles inside the liquid oxygen tank for the first stage, but on our second stage, we're actually storing them inside the methane tank.
Terran R uses a combination of saturated and subcooled propellants. This gives us the best blend of performance and operational ease.
Moving up the vehicle towards interstage, you'll see 4 perimeter tension latches, but we're going to be pushing through the center. So we're going to have a center pusher that is going to be guiding the second stage nozzle out of the interstage during stage separation. A lot of the magic for entry, descent, and landing happen after stage separation for the first stage. After the first stage separates, we use cold gas thrusters to flip the vehicle over and orient it for its entry burn. But while we're doing that, we're also being very careful about not letting the propellant migrate too far forward into the propellant tanks, mixing with the ullage. Once that's ready to go, we turn the engines on to slow the vehicle down, preparing it to enter the atmosphere. And the reason why we do this is we don't want it to burn up in the atmosphere because the heating environments are very high. During entry aerodynamics, we use the grid fins and the vehicle body aero to slow the vehicle down in conjunction with its thermal protection system. It enters its landing burn configuration where we look to deploy the landing legs and also finally slow the vehicle down to its final descent onto a barge. During aerodynamic re-entry, we'll rely heavily on our in-house developed thermal protection system. We're leveraging material science in that area to give us the lightest weight, highest performing material we can get while still meeting the requirements of rapid reusability. There's a lot of proprietary work that's going into that material development, but it's an area that I'm quite proud of as well. The other area that's going quite well is a lot of our in-house kind of homebrew GNC algorithms, software, and codes. We have a very strong GNC team here that has both a mixture of experience both in and outside the industry. The GNC team has developed algorithms for engine control, mid-flight guidance, and day-of-launch trajectory designs. Recently, our Terran R flight software teams reached orbit with our HOODLE test, and now HIDL is also underway.
We're making a tremendous amount of progress on our ascent, reentry, and landing algorithms. Utilizing the Terran 1 guidance, navigation, and control heritage allows us to develop the algorithms necessary for Terran R much more quickly and efficiently.
The other area that I'm really proud of for the team is just how many of our mechanisms and valves and components we design in-house and test. So for example, our thrust vector control, our engine throttle valves, a lot of the solenoid valves. These are things that our team is really doing a bang-up job of designing and manufacturing and testing ourselves.
There's a huge buzz about the factory. Every day new flight hardware is beginning to be produced. Flight software is being released. Test and launch infrastructure is being built, and we're making great progress towards launch.
Product development essentially means all the steps you take from the idea of a product to actually putting it in the market for your customers. If you look at the approach we're taking for Terran R's product development versus some of our competitors, I'd like to break it down by 3 or 4 different categories of the approach. One is the scope and the sequence of all the work going on in development. Another one is how much analysis or simulation that a team will do to predict things before they actually will experience them. And the third one, how much content is in the first vehicle versus the end state vehicle as you get further into the life cycle of the product.
The traditional approach to product development in aerospace is extremely serial. You'd have a whole design and development flow that results in a qualification design that you take through a qualification campaign, and only at that point would you really kick off full flight production. You do a lot of acceptance testing and testing at component level. That way you minimize the risk to your stage campaign, but you also push those things out because you need to get through all of these component level qualification and acceptance tests before you're willing to go to stage test.
If you look at a lot of the very risky startups that are out there in the launch industry, a lot of them aren't doing a lot of testing at smaller levels of assembly. They're trying just to get to the launch pad or to a stage test, and they're also not reusable. So in that sort of environment, it's very hard to learn as you go. There may be a lot of surprises that you find because individual high-risk items weren't studied in advance or tested in advance, and that can lead to a pretty tough stage test campaign or even the loss of the vehicle pretty early in a mission. And we've seen that in the industry time and time again. So when we look at the Terran R approach, we're trying to optimize between those two and learn where we need to at the small scale where it's less expensive, but still pull the learning from working at the full scale ahead as fast as we can.
So what that means for us is that because we need to start building flight parts before we've completed all of our qualification, we may need to include some adjustability or optionality in the design that actually gets released. We also try to leverage acceptance testing at the system level where we think that's appropriate. We may not ATP every single component before we go to an engine test or a stage test if a component failure during that higher level test is not going to be catastrophic. We believe that full-scale testing at the stage level or as high a level of integration as you can is really the best way to learn about your design. We're focused on trying to accelerate to those huge proof points as fast as possible. We really depend on the experience of our leadership and our senior engineering team to know what are the smart risks to take versus what are the things that we really need to get right up front. The fastest path to first flight is not a one-size-fits-all answer. We really need to tailor our approach to each subsystem based on the criticality, the fault tolerance, how much you need to test, etc. Something like the primary structure is more amenable to analysis and you really don't have time to iterate it. So you've got to get that right the first time. That goes through a more rigorous analysis and qualification approach than something like, say, an avionics box that you do have a chance to iterate if you need to. We do test those things at the component level, but the design cycle is much shorter, so we may not spend as much time in analysis. And then the engine obviously has a high dependence on test. There's things that we can only learn on the test stand, and it's going to have to be an iterative design. So in the engine team, we really focus on getting things out to test quickly rather than spending our time in analysis, learning on the test stand and iterating the design that way.
Having a manufacturing strategy that's aligned with our need to develop the product quickly and get to the right risk level for our customers, that's really the name of the game. In areas where we know we need to iterate to learn, we use manufacturing processes that are really nimble. And the main area for that is our propulsion system. Using a combination of powder bed fusion and WAM technology and then some other techniques that we might be the first in the world to use, we are able to learn really quickly on our test stands and also through design and analysis, make changes, get back to the test stand and get closer to that really end goal product. And then similarly, when it comes to things that are very long lead items where we don't have the opportunity to iterate as much like primary structure, we use techniques where we know the reliability is very high. Traditional methods that you might see on other rockets, we use those too, and then we put our own special spin on it.
We're optimizing for the things that matter to our business. Speed of getting the product out the door and getting customers on board, payload to orbit, and reusability, which unlocks the economics that we really need for long-term success. That means that when we're assessing technologies, we're not necessarily looking at what's the most advanced thing out there. We're looking at the things that meet those needs. How do we get a reusable vehicle out there quickly so we can start flying customers?
Across the Terran R program, every single decision, every single engineer or technician is focused on what we call the food, water, shelter of rockets, which are performance to orbit, development time, and the cost of whatever component or system they're developing. We try to make it very clear that even if one system is not hitting its own perfect targets, if we're delivering that target for our customer at the end of the day, then we're still being successful.
You can't just focus on speed to first launch though. The long-term key to this program is really reusability and payload performance to orbit. We do have to find the right key drivers within the design for getting to reusability quickly and the key drivers for performance. And those things are going to require more attention and more upfront investment than things that are still required to fly, but maybe less critical to the long-term success of the program.
So when we look at the balance of getting to a first launch and serving our very first customer in the launch business of Relativity versus developing a reusable high cadence vehicle for the future, the approach that I recommend is to try and make them the same thing. There may be some cases where we make a decision on a small part of the first rocket that isn't perfect to fly 50 times a year. But by learning on that first one, we will go faster to the second or third iteration of that part or system to actually hit the high cadence. My job really overall is to find those opportunities to pull the learning ahead and then make the goal the same, even though we have different outcomes in different parts of the program.
So I think one of the most misunderstood things about Relativity has been, why were we 3D printing barrel sections on a rocket with Terran 1? So when I started the company 9 years ago, we knew that additive manufacturing was really only able to build about a cubic foot in scale. So I thought with a bunch of smart people and a bunch of time, we could really push the boundaries of what that technology was capable of. And we did just that. We built a rocket that was 85% 3D printed, launched it to space. We proved the viability of our additive manufacturing tech.
Coming off of the Terran 1 program, where the primary tanks were wire arc additive manufactured, we reviewed that decision again and for the Terran R program. And coming out of that trade, we felt that for the Terran R program, right now and right today, friction stir welded aluminum alloy tanks are the best choice for us right now. And so at Relativity Space, we're not afraid of changing and pivoting where we need to meet our development goals. And our development goal, to be really clear, is to field a very commercially viable, high-performing vehicle. And so we're not dogmatic about how anything should be made or the history of the history of the company or anything like that. We're just dogmatic about fielding a great product.
Our manufacturing methods are a trade like anything else on the vehicle, and it's really important to understand the pros, cons, and risks of every trade. And so when we look at a manufacturing method that could be as impactful as how we're making the barrels or the domes or the fairings, this really comes down to a balanced approach between engineering, supply chain, manufacturing, and the global business. Smart decision-making is optimizing for the entire business, not just focusing energy in one particular area that we may optimize locally.
The latest tool at the time that's going to be the best choice for manufacturing is what we're going to use. And we initially set out to try to print the domes. We quite frankly struggled to get that process at rate high enough to really kind of fit the commercial needs of this vehicle. So from there, we pivoted to more traditional aluminum lithium alloy domes. And we're partnering with a supplier to help us develop them.
So the domes that we're buying are some of the most advanced that have ever been produced. I have personally seen domes produced 4 different ways for different launch vehicles. And this is one of the most performant production methods I have ever seen. And this outside vendor being really good partners with us. They want to scale with us. They want to invest in our business. They want to share their learning, and they want to help Terran R succeed. This is where we had to make a smart decision for our business and truly a smart decision for our customers' business.
Any successful development program that I've ever been a part of or ever seen really didn't have a perfectly straight and narrow path right to developing that great product. And I think what defines kind of the success of companies and programs isn't necessarily how many great choices the company made out of the gate. It's really the agility and ability of the staff and the team to pivot as quickly as possible and still drive progress, and quite frankly, not be fazed by change. Sometimes development is running down the wrong path as quickly as possible to then pull yourself out of that path as quickly as possible to get on the right path.
We have gotten farther in 3D printing because we invested in those domes, and we're using that 3D printing technology elsewhere.
We're still using additive manufacturing on Terran R in areas where it really helps us. You know, things we're looking at are areas that help us get to market faster, develop, build, and test faster. WAM has been a big part of our engine program since the onset. We use WAM to clad our outer jacket for pressure capabilities on the main combustion chamber.
I think we're seeing some tension between how we would optimize Terran R from an engineering perspective, from a technology perspective, and how we would optimize it from a business perspective. It's not uncommon that a company such as ourselves needs to strike a balance between those things. When we think about the long-term trajectory of Terran R, much technology development will occur, many insourcing decisions will occur. Those are not necessarily the right trade for the business today. The manufacturing processes are on the front lines of that tension, of those decisions we have to make between what technology do we want to push ourselves and where do we need to compromise perhaps to advance the business goals.
And I think the fairing falls into that category. It's a very large structure, and also the separation mechanics and the multi-body dynamics of having the fairing separate cleanly, getting the fairing qualified, also the fairing acoustic performance, in addition to heating performance. Those are all very tricky engineering things to get right. And quite frankly, I feel very fortunate to have a partner that can help us build our first fairings.
And so for our business, it's really a question of, do we want to spend our resources and our time that way? And is it right for the customer trade? Does it matter for their objectives that we build our own fairing? Or can we start delivering on our customer demands faster by partnering with a company who can provide us some of the experience and production capability on a fairing system?
The COPVs were a similar trade-off. It will be more beneficial to the program right now for sake of execution speed to partner with a vendor to get our COPVs off the ground. Every decision, both technical and non-technical, we have our customers in mind. We're developing this vehicle to be a commercial workhorse that can really help support and deploy customer constellations or satellites, and for their own businesses.
Aeon R is a GG cycle LOX LNG or LOX methane engine. Produces about 270,000 pounds of thrust at sea level. We have 13 Aeon R engines on our first stage, and we have a single vacuum variant on our second stage that produces about 323,000 pounds of thrust.
What it does is we feed fuel and oxygen in a fuel-rich mixture ratio to the gas generator, which is then ignited by gaseous hydrogen and gaseous oxygen, which jump starts the gas generator ignition. That provides exhaust gas that is fuel-rich to the turbine wheels that spins the pump. That, however, is not enough to jump start the engine, so we supplement that force with high-pressure nitrogen, which blows into the turbine wheel, the turbine exhaust, and spin starts the engine. That gas generator then spins the pumps, which pulls propellant from the vehicle, liquid oxygen and liquid natural gas, into the combustion chambers for the engine and provides thrust.
Terran R program leverages densified propellant, or propellant that's cooled below its saturation temperature at ambient pressure. This is really important to the capability of the vehicle because it allows us to get more propellant mass in the same size tank, and it also provides us better thermal margin to saturation or cavitation when we're operating the engine.
You have two different variants of Aeon R on Terran R. You have the Stage 1 engine, which is designed to operate at sea level for the most amount of thrust at the most critical time, which is liftoff. Then you have an upper stage engine, which is Aeon R vacuum, which is designed to operate in the vacuum of space. Aeon R Stage 1, Aeon R vacuum look very similar. There is one major difference between them, and that is the nozzle.
Aeon R leverages a lot of the learning that we gained from Aeon 1. It's the same cycle, gas generator, and uses the same propellants, LOX and LNG. But Aeon R is a much larger engine with much higher thrust, and also requires us to have throttle and MR control in order to meet the mission of the Terran R vehicle. So we structured the entire Aeon R program around several iterations, and that also informed our choice of manufacturing technologies. By leveraging additive, we're able to quickly make changes to key components like the combustion chamber, the injector, the pump, learn from test, deploy a new design, rinse and repeat. We use powder bed fusion or PBF printing for a lot of our complicated fluid components. We also use the wire arc additive manufacturing, or WAM technology, that we developed from Terran 1 for cladding and feature buildup on our combustion chamber. Overall, we have 4 main iterations of the Aeon R engine. The first was ultimately a manufacturing demonstrator and a chance for us to go and try to build this much larger, more complex hardware. We called that AR 1.1. The second iteration, AR 1.2, is what we tested in late 2023. This was able to hit the state point of the engine, hit the thrust and MR that we were trying to hit, but it was not a flight-like package and it wasn't capable of gimbaling. We had a number of engine failures in AR 1.2 that really gave us the key learning that we needed to build a more robust, high-performance product in AR 1.3 and beyond. We were able to meet our MDC milestone with the AR 1.2 iteration, which was the first one that we got onto the test stand. I think that's really a testament to the quality and experience of the team, as well as the key choices that we made on engine cycle and propellants in order to leverage our previous learning.
The very first time you start testing a rocket engine, you should expect failure. Part of the process for developing an engine is ensuring that your block upgrades as you go through the development process include that expectation of failure. If you know your first engine is going to fail, which it will, you focus on the developmental areas that are the hardest to obtain. Startup, shutdown, throttling. Don't combine all of the additional pieces that you can learn on a bench somewhere else.
One of the key advantages of the GG cycle is that you can get really high quality data from component testing of your TCA and your gas generator. And that set a foundation for us to stretch even higher and push for higher on performance. AR 1.3, which we've been testing in late 2024 into 2025, is really a flight-like engine design. It fits the vehicle package, it's capable of gimbaling, it has our full-size engine skirts, so we're hitting our full thrust and full MR, and it has all the features that the vehicle needs as well, including pressure and heat exchangers. Maybe most importantly, AR 1.3 also included flight-like avionics and a flight intent software stack. This is the first chance for the Terran R program to really demonstrate this full end-to-end capability. We use an engine controller that controls the startup and shutdown sequence, as well as closes the loop on throttle for vehicle throttle control. We're getting all of our last little changes in, we're dialing in the operating point that we're going to use to qualify the engine, and then we're going to roll that all into our AR 1.4 iteration, which will qualify and we intend to fly.
Where a dev campaign paints where the engine operates, the qual paints where the engine should run in flight and establish that life expectancy. If you know the total life expectancy of an engine is 2 tests for acceptance testing in Stennis, and then 1 static fire prior to launch, and then a total stage 1 ascent, and then a relight, and then a landing burn. You take all of those starts and all of those run times and you build them together into your program. And your qual program basically says this engine can operate under those specific conditions as many times as we need it to. Aeon R is designed for reuse in mind from the beginning, so our intention is from very early flights to be able to recover stage 1. What that essentially means that the engine has to relight in space on its way down. What that requires is a very simple approach in the design to ensure that complexity does not add failure mode. A hydrogen-oxygen ignition system for the gas generator and a spin start is a very stable, simple approach to relighting an engine. That simplistic approach is usually the best for ensuring reusability and reliability, which is probably one of the most important components of stage 1 that function on relight.
Any difference between the way you test your engine and the way you operate them in flight is an opportunity for an issue or a failure mode that you didn't see in test to crop up and keep your vehicle from working on the day that matters. This means that we need to really understand how the engine is operated on the vehicle, what its environment is going to be on the vehicle, and then investing in our test capabilities to make sure that we can do exactly the same thing on the ground. We have both the engine team, the test team, as well as our mission reliability team constantly looking, what are the test like you fly deviations? What are we not anticipating? How can we eliminate those before we get the stage test? We think this is really going to help us move faster through stage testing and have a more successful launch.
There's an industry term called test like you fly, which I've always thought is a little backwards. It actually should be you fly like you tested. When you test the rocket, you're bounding what you know the rocket is capable of doing reliably. I know the rocket will light at this temperature. I know the rocket will fly at this pressure. I'm confident the systems work there. And then you should baseline what you think the flight profile will stress the rocket to, and then test to a larger window than that to ensure that you're not doing anything for the first time when you release the rocket for flight.
2025 is going to be an exciting year because we have the full definition of the vehicle. We're moving on. We will have qualification engines in Stennis going through testing. That's going to qualify our flight design and unlock the ability to go produce flight engines at rate. We'll have the primary structure completed for parts of our rocket. We'll begin integrating on what's often called the secondary assemblies, avionics, fluids, propulsion systems. We will see the entire factory, every single work center become alive. We will see hardware flow from one work center to the other. We'll lean on our digital systems, our enterprise systems. This is truly the first year we're going to have a fully functioning factory for Terran R.
And on the manufacturing side, the manufacturing teams have been hard at work, getting this production facility operational. And also, in addition to that, there's a lot of infrastructure that's being put in to turn on our machine shop in a higher capacity to produce more hardware.
Not only are we building out each work center, we're building out the capability of each work center and the capacity analysis of how these work centers optimize for themselves and flow into each and every other work center. This is a foundational element of a mature production system. The entire process starts with raw material arriving on the dock. We then mill out the panels ourselves, removing mass where we can to both optimize for strength and optimize for mass. We go through a rolling process where we take these panels and bring them as close to cylindrical geometry as we can. It doesn't have to be perfect because the friction stir welders that we've designed have the ability through the tooling and through different clamping methods to bring approximately cylindrical barrel sections into the correct tolerances where then we can proceed through the friction stir welding operation. We start vertical, we make one barrel. Then, as we have barrels stacked up, we can go through a circumferential welding process where we complete a much longer cylinder than we would be able to complete with a pure vertical welding method. From there, we're able to add the end caps for domes also through a friction stir welding process, and that completes the tank for the primary structure. But a lot of the way this is built for our panels, the way we have to incorporate our design features, the weld parameters that matter for the alloys that we're using, this is all customization that is not available off the shelf. 2026 is bringing it all together, all elements of the vehicle.
The second half of a development campaign, essentially between the critical design review that we just passed in December and first flight, is one of my favorite parts of the entire industry. Some of the things that I look forward to the most are completing our primary structures testing. These are some of the most complicated tests we'll ever run, with millions of pounds on the rocket at dozens of PSI of pressure, really pushing the limits of what structures can do. We'll learn a lot from those before we go to stage testing. Stage testing, in my mind, is really where the rubber hits the road for the program. It's the first time that every piece of the program is united together across hardware, software, avionics, propulsion, structures, mechanisms, and the infrastructure teams. So that's really, in a sense, a dress rehearsal before our launch, where we can see the entire system and all of our teams come together. And I think that's personally my favorite part. And then from there, there's nothing like getting into a launch campaign, getting the whole system together, and again, uniting the teams. The focus that you have in that final phase of the program is a feeling that I always look to find in my career, and I'm really excited to get there this time.
The first steps after our first launch have already begun. We're already working on the second flight worth of hardware in some cases. Over 2025 and 2026, we'll have multiple ship sets of Terran R hardware in development so that we can follow up our first launch as quickly as possible with a second launch, third flight, fourth flight, and beyond.
Looking ahead to our long-term ramp rate, you realize that manufacturing and scaling of hardware production is only half of the equation. The other half of the equation really is tied to how rapid reusable this vehicle is.
Reusability is one of the top goals of Terran R, even in the early days. From the very first sketches of Terran R that I did with a few folks, we've always been focused on getting to first flight fast, but making sure the architecture is extremely sound to make the vehicle reusable as fast as possible. One of the fundamental requirements of any reusable booster system is the capability to complete entry, descent, and landing, which in the industry we call EDL. And there are three main things any system needs to do to get there. First, it has to slow down from an extremely high velocity after the end of the first stage burn per ascent, somewhere around 4,000 or 5,000 miles an hour. It then needs to survive the physical environment of entering the atmosphere and slowing down from that high speed, which creates extreme levels of heating, thus temperature and vibration on every system of the rocket. And it needs to slow down and accurately hit the landing location, which in our case is a barge floating in the Atlantic Ocean.
The vehicle architecture is set up in a way where it's got reusability in mind right out of the gate. There are a lot of ways that this manifests. I think the first one in my mind as a rocket engineer is vehicle performance. we allocate a lot of rocket performance towards recoverability and reusability. I think the other areas that our designs out of the gate are kind of implementing those features right away. Our grid fins, for example, are there right away. Our landing legs are right away. And we're already thinking about how this vehicle operationally is going to perform for recoverability.
Because the vision for Terran R has always involved reusability, we've invested a lot of resources in understanding reusability and developing the booster architecture to allow reuse in the early days. One of the areas that is really essential to entry, descent, landing success is aerodynamics. So we completed a full test campaign for both the aft end of the rocket, which is a very sensitive area in terms of loads and heating, as well as tests to understand our grid fin control system years in advance of our first flight. So our approach to realizing the full potential of Terran R involves a block upgrade strategy. This essentially means that we'll stage different changes of the vehicle and the ground systems over time to finally get to the full potential later on. And this is critical to the overall success of Terran R because it allows for learning in the early phases of the program while we can still serve customers without requiring us to get every single thing perfect.
The vehicle iteration is a really important part of our development path. Our development path doesn't stop at the Block 1 vehicle. We're already thinking about Block 2 and Block 3 and beyond and what that vehicle looks like. But you have to be very, very careful when you're looking at these upgrade paths, because if you make your first block too ambitious, too high performing, you're less likely to field it in a reasonable amount of time. What we've chosen here to do is just make the targets just a little bit easier on our team and shoot for, let's say, 20 tons, metric tons to low Earth orbit for our Block 1 vehicle, and aiming to work through our reusability and recovery plans in our operations and in our testing for the first block.
In Block 1, our goals are very simple. We need to get our customers to orbit safely, and we need to recover boosters. And the focus there is really on making Relativity into a new launch company in the market and starting to learn about reusability and operations to get ready for future parts of the program.
We're going to try to soft land the first stage for the first mission in the ocean. I think coming out of the Block 1 campaign, we'll want to have recovered and fully inspected and potentially retested a first stage that we've recovered, but we're really not leaning on true reusability for the first block of the vehicle. The first block of the vehicle I really view as more of a engineering stepping stone to get to the full reusability of the first stage.
Block 2 builds upon the lessons we learned in Block 1, specifically around collecting flight data for ascent to expand our mission capability to serve different parts of the customer marketplace, and also to move into reuse, not just entry, descent, landing of our booster stage. So that's really a place where we go from learning to execution and beginning to refine the system overall. From Block 2, we know that there's still potential in our architecture to fly higher performing missions and expand our mission set, and we'll get into that in Block 3. Similarly, as we get into reusability, not just entry, descent, landing in Block 2, we'll take those lessons to get to the highest cadence possible for the overall system in Block 3, where we're talking about 50 or even 100 flights a year. Even though Block 1 might start with relatively humble goals looking at the overall industry of getting to orbit and getting to reusability, the vehicle architecture has been developed in a way where the full potential will allow us to do things that no one has ever done.
There's a augmentation of terrestrial telco in space, and it's happening through low Earth orbit constellations. And so these are very much like what Starlink is doing. There are folks like Amazon have announced constellations in low Earth orbit, and our vehicle, Terran R, is geared to serving primarily constellations that are trying to put up thousands of satellites up in orbit, generally anywhere from 500 kilograms to something like a ton or a ton and a half in terms of weight and the associated volume.
Now you have several mega constellations in development, with additional customers each year coming up with new concepts for direct-to-cell phone constellations, broadband constellations, additional Earth observation constellations, all leading to very rapid growth. And really what we're seeing is the market over the next several years is growing several-fold. Terran R has been designed to carry 20,000 kilograms to low Earth orbit. That's really what we've identified as the sweet spot within the constellation market. It's large enough to provide great economics on a dollar per satellite basis, but small enough to ensure that we're able to fill it full with each launch.
Some other launch vehicles are much larger, but they run into the challenge of not being able to fill the launch vehicles. They're flying half empty or even more. Some vehicles are much smaller and end up with a much higher cost per satellite to space and require many more launches to deploy the same constellation. It's really from the beginning been this trade of optimizing the size vehicle to meet the constellations that we see coming to market. I've always been a firm believer that you need to work with customers from day one to make sure that the product you're developing actually solves their needs. From the very inception of Terran R, we've been out engaging with the largest commercial operators around the globe early, often every quarter, meeting with them to make sure that each design choice that we're making was servicing the market that's growing today. Customers are looking for several things. First, they're looking for the company that can offer the best economics, so the lowest dollar per satellite to space. Second, most of these customers don't just need one launch, they need many launches. And so they're looking for a company that's developing a full launch system with a higher rate operations in mind. They also look at, are you developing a launch system that can operate with enough capacity to actually matter to the market? The market's growing very quickly, and you need to be able to ramp your launch cadence quickly as well to have a meaningful impact in the market and justify them betting on a single company. And finally, they're looking for a partner that they can rely on, that's got a team that they can trust, and that's got a business model that is incentivized to support them, not compete with them. The feedback that we've gotten from our customers over the last couple of years is that we have built tremendous amounts of trust based on being very transparent about what we're building, why we're building it, and then delivering on our promises, which is, again, why we've created the $2.9 billion backlog that we've signed to date.
It's really important that they have a partner and a vehicle that can service their needs in a narrow window, or that window and the market opportunity candidly won't exist. Reuse is absolutely critical to the economics, but reuse is also absolutely critical to ramp rate, because in order to launch dozens of times a year, if you've got to build first stages with the number of engines and the complexity on the first stage dozens of times, you're just not going to physically be able to do it.
What we're seeing today is demand that is growing faster than any one supplier can possibly serve. In addition, we're also hearing from customers a very strong desire to ensure that they have multiple options to get to space. Really what we're seeing is the market over the next several years is growing several-fold.
You've heard from many of our great leaders, and you've seen the progress across the vehicle and our critical test and launch sites. I'm really excited to be here. I'm really excited for what's ahead at Relativity, and I hope you join us and stay tuned as we march towards our first flight.